Welcome to this video more about resistance and resistivity. In this video, I'm going to pick up from where we left off, which was a very vague definition of resistance, and get into a little bit more detail and kind of propel us on with a few more questions. So I'm going to pull you back for a second to the capacitor. Remember, this was a passive circuit element, and the capacitor was, or the capacitance of the capacitor was defined as the amount of charge that could be stored per volt across the capacitor. This in unit form was coulombs per volt, which was a farad. Now we found that the capacitance itself of the capacitor was not defined by how much charge was on it, or was not defined by how much voltage was across it. It was actually defined by the amount of material it was filled, or the kind of material it was filled with, the dielectric constant, times vacuum permittivity, times a ratio of something geometrical about it, in this case for a parallel plate capacitor. So here I have a material description, and here I have a geometric description. And the reason that I bring this up, even though a resistor is completely different to a capacitor, we have very similar structural ideas, is material and geometric components are going to define what the resistance is. So when I think of a resistor, from the end of the last video, we defined resistance as that ratio of the potential difference across the material or across the object, right, to the amount of current running through the object. And this was a volt per amp, which we called an ohm, symbolized with the Greek letter uppercase omega. What we're going to see very similar to the capacitor now is that a resistor actually has some sort of material, or the resistance of a resistor has some sort of material dependence and some sort of geometric dependence. And that's what we're going to look at first. The material dependence is described with the term resistivity. So resistivity describes a material, not really the object, but the resistance overall describes the entire object. Similarly here, the capacitance is describing the value for the entire capacitor. The material inside the capacitor, right, determines the capacitance. And so what we're going to look at here is this term resistivity, and I think it's best understood if we compare it to the term conductivity, because both of those words have roots that we all, I think, understand. And so when we think of a good conductor, this allows the flow of electricity very easy, right? Electrons are allowed to flow. Whereas we could think of resistivity as the opposite of, or the antonym to, conductivity. Conductivity will use the symbol sigma. Resistivity will use the symbol rho. So if you think about it, if I had something that was very low conductivity, it would have a high resistivity. And the more resistivity the material had, the more resistance it would offer. So I'm going to put the rho here as directly proportional to the resistance. Now we can take a look at how the potential difference across the resistor is affected by how much resistance there actually, or resistivity there is in the material, by taking a look at the awesome simulations from the fet.colorado.edu website. So if I attach the voltmeter across this wire here, remember all material and all objects have some kind of resistance, whether they're being intended to be used as resistors or not. So if I look at this over here, I see right now that the resistivity of the material of the wire is set to basically 0. So what that's saying is that there is a high conductivity, and thus nothing is really slowing down in this piece of wire. Now I'm going to look at it from this perspective. In order to push an electron through here, we have to have a certain strength of electric field. And right now, we have a very low wire resistivity, a high conductivity, and so there's not really any extra push needed to get the electrons to move besides just having something to give them kinetic energy. Now, if I increase the resistivity or decrease the conductivity, so basically this would be like going from making the wire from something that has really good conduction, like maybe aluminum or silver, and making it into a wire that's not really desirable most of the time. This would be increasing how insulating the wire is. Now, we're not talking about the coating outside the wire, we're actually talking about the wire itself, which doesn't really make a lot of sense. And that's what we're trying to get across here, is that the idea of the wire is not to resist. We want to have as little resistance in the wire as possible so that we can use that energy more for the other things that were connected into the circuit. The wire here is really just a conduit to help us move the electricity into some other energy form. But if I increase the resistivity of the wires, we see here that what it's showing is that in order to have some amount of current through this material, or through this object, this piece of wire, there's going to be a certain amount of voltage paid to pass through this. And so when I look at it from that perspective, I can see that the resistivity is directly proportional to how much resistance is across this wire. Now, if I extend the length of the wire, we can think about how in the capacitor, by separating the capacitor plates, when it was not connected to the power supply, you adjusted the capacitance. And we see the same thing happening here again. The voltage is actually increased across this object with the same resistivity. So in other words, what I'm saying now is that in order to get electrons from one end to the other, you need a much greater potential difference to achieve the movement between the two sides. So the length of the resistor, or the length of the object, is also going to be directly proportional. And here again we're looking at the geometric part of the resistance. The length, the longer it is, the more material there is, and the more material there is, I will have a greater resistance. Now, one thing I can't show on this particular simulator, although there is another one that you could look at, is actually the cross-sectional area of the wire. Now, because I'm not getting into the details about current density and resistivity from that perspective, all I'm going to say here is, if you think about it, if I make this wire longer, but then I widen it, I'm actually allowing for better flow of the electrons. So the area, the cross-sectional area of the wire, is actually going to be inversely proportional to the resistance, because the wider the wire, the greater it conducts. And so I'm going to use L over A to represent that. So here I have a very useful relationship between the material and the geometric structure of a resistor and how that affects the resistance of the resistor. Now, what's going to become very interesting, and we'll look at in the next video, is the idea of what is known as Ohm's law. Georg Ohm is who this law is attributed to, and it's oftentimes misinterpreted a little bit, and we're going to look at that in some greater detail. And the reason for that is Ohm's law relates current and voltage to one another when resistance of the material, or the resistance of the resistor, is independent of the current and the voltage. In other words, let's imagine I had this circuit here where every time I applied a greater potential by the battery, so a stronger potential difference across the circuit, the current went up. But every time the current went up, it affected the material in the circuit. That would cause some kind of double effect, if you will. So not only is the material itself affecting its resistance, but every time I add current to the circuit, it's also going to affect the resistance, and that's going to cause a change in the resistance of the circuit. This is what we refer to objects as being ohmic or non-ohmic. And that's going to be the topic for the next video.